Ever been on a seesaw? You go up, your friend goes down. The movement can be in both directions. But there is always a point in the middle where everything is balanced. Now imagine if you had a smart sensor that detects how far up or down the seesaw moves and sets off an alarm if it goes too high or too low. That's what exactly we are going to do today. But instead of kids on a seesaw, we are tracking electrical current in both directions, which is called bidirectional current sensing circuit with a window comparator. By the end of this video, we'll understand how this circuit works, why it's super useful, and how to design one yourself. So, let's start. If you ever felt stuck between your circuit ideas and an actual working PCB, then let me introduce our partner of today's video, which is Altium. Altium Designer is a complete PCB design tool where we capture schematic, design PCB layout, run simulations, and create manufacturing ready electronic circuit all in one software. It starts with schematic capture, where we transform our paper circuit to a proper design, which is ready for simulation and layout. Then we can run SPICE simulations to test our design, to check the performance and catch any mistakes before they cost us time and money. And after that, we can directly optimize component placement on PCB and design layout with advanced routing tools. It even helps with wiring harness design, where we can plan, design, and document our wiring harness, which connect PCBs with each other. And now it gets even better with Altium 365, which connects our design to our teams, manufacturer, and even component suppliers through cloud. With this, our team can review, comment, and collaborate on the projects from anywhere in the world. Very important feature is its BOM portal. It keeps our component sourcing organized, where we can track component availability, compare suppliers, and check if we got the right parts before placing an order. So remember, Altium Designer is where we design our electronics, and Altium 365 is how we connect with the team to build the project into reality. And the best part is you can try Altium Designer for free, and when you buy the license, you get 25% discount. You just have to click the link pasted below in the description. So now on the video. For example, you have a solar power system installed at your home. During the day, sunlight strikes the solar panels, generating electricity. This power is sent to the charge controller, which regulates voltage and current. The battery stores excessive energy to use it later. Here, current flows in one direction from the solar panel to the battery, and if this charge controller provides very high current, then battery could damage because of the overcurrent. So, we need an overcurrent protection. Now, during night time, there is no sunlight, so the solar panels stop generating electricity. Your home still needs power, right? So the battery starts supplying stored energy to appliances, and due to some excessive use and high power, if there is any short circuit or the current is going beyond safe limits, then the battery could damage. So we have to monitor the current which is flowing in the opposite direction as well. That's where this bidirectional current sensor with a window comparator comes into picture. Imagine you are a traffic cop monitoring the flow of cars on a busy street. You need to know not only how many cars are passing by, but also in which direction. That's essentially what the circuit does, but with electrical current. In technical terms, it measures the current flowing through a load by monitoring the voltage across a low value resistor called a shunt resistor. This setup helps us detect the current flow in both directions. So it is called as bidirectional. A window comparator acts like a safety barrier. It monitors a signal and alerts us if it exceeds predefined limits. In our case, if the current is too high, then it gives an overcurrent warning. If the current is too low or negative beyond a limit, then it gives an undercurrent warning. And why is it called a window comparator? because it defines a safe window for the current. As long as current is staying inside this window, everything is fine. But if it goes outside, an alert is triggered. So it is a two-stage circuit. First stage is the bidirectional current sensor and provides proportional sensor output to the second stage, which is a window comparator circuit. So this full circuit measures current flowing in both directions and triggers alert when the current exceeds predefined limits. We have already seen how bidirectional current sensor circuit can be designed using TI's INA240A1 current sense amplifier in this video. If you want to check that, you can click on this card. The two comparator circuits compare the amplified output voltage coming from this CSA against two reference thresholds. First is the lower threshold voltage. If the current drops below this level, the comparator triggers an overcurrent alert. And second, higher threshold voltage. If the current exceeds this level, the comparator triggers an overcurrent alert. Let's see how we can design such a circuit. Our goal is to set up a window comparator that checks whether the current flowing through our system is within a safe operating range. If it crosses this range, the circuit triggers an alert to protect the system. Let's break this down step by step. First is the rising overcurrent threshold. If the system current exceeds 100 ampere, the circuit detects this as a rising overcurrent condition. This means that too much current is flowing in the forward direction, which could indicate a short circuit or excessive load. At this point, the comparator circuit activates an alert to indicate that system is experiencing an overcurrent condition. Once an overcurrent condition is detected, we don't want the system to stay in an alert state forever. Instead, the system must recover when the current drops back to a safe level. For this design, the system recovers when the current drops below 90 amperes. This means that once the current decreases back to a manageable level, the comparator resets and normal operation resumes. We also need to monitor when excessive current is flowing in a reverse direction. For example, if the current drops below minus 35 amperes, it means that too much current is flowing in the reverse direction. When this happens, the comparator circuit triggers an alert warning the system that we have a reverse overcurrent. Here also, the circuit needs to recover from our reverse overcurrent fault. The system must detect when the current resumes to a safer level. For this circuit, once the current rises back to minus 31 amperes, the system considers the condition resolved and alert is cleared. And we will provide a supply of 3.3 volts to this whole circuit. Now that we understand the design goals, like triggering alert when current goes above 100 amperes or below minus 35 amperes, let's figure out how the circuit knows when that happens. To do that, we need to calculate the output of our current sense amplifier, the INA240A1, at those exact current thresholds. This output voltage is what will feed into the window comparator. So let's dive into the math that makes this happen. This amplifier measures the voltage across a small resistor called a shunt resistor placed in the current path. In this design, we'll use a 0.33 milliohm resistor, which is very tiny but perfect for high current measurements without wasting so much energy. The formula for the amplifier output voltage is this, where G is the gain of the amplifier. We get this gain from the datasheet of the current sense amplifier. In our case, we'll use which gives a gain of 20. This is the differential voltage across the shunt resistor. Vref is the reference voltage at the output when the current is 0 amperes. In our circuit, we are powering everything from 3.3 volts. The reference voltage is set to half of the supply. So we get a centered bidirectional output range. This means when there is no current flowing, the output of the current sense amplifier sits exactly at 1.65 volt. If the current flows in forward direction, the output rises above 1.65 volt. If it flows backwards, then the output drops below it. We use simple Ohm's law to calculate the voltage drop across the shunt resistor. Let's put that into a formula to find out the output voltages at our different current levels. Overcurrent threshold in forward direction. So when 100 amperes of current flows, then the output voltage becomes 2.31 volts. This is rising overcurrent threshold. At 90 amperes, the output voltage is 2.244 volts. This is the point where the system recovers from an overcurrent alert. When minus 35 ampere current flows in reverse direction, the output drops to this value, which is our falling overcurrent threshold. So at minus 31.5 amperes, we get 1.442 volts, which is our recovery threshold in the reverse direction. Each of these output voltages becomes a trigger point for a window comparator circuit. If the output of the current sense amplifier goes above 2.31 volt, the system knows that the current exceeds 100 ampere and an overcurrent alert is triggered. If the output voltage drops below 1.419 volt, the system detects a reverse overcurrent. When the voltage returns between 2.44 volts and 1.442 volts, the comparator outputs go low, meaning the fault is cleared and the system resumes normal operation. After this, the next step is to design the register network that sets the comparator trigger points. This means we'll calculate the exact register values that makes the comparators turn on or off when the sensed current crosses our threshold. Let's walk through how that's done using a combination of voltage divider math, comparator theory, and some basic algebra. Let's start with this comparator, which detects the reverse overcurrent condition. We assume R2 as 10 kilo ohms as the bottom resistor in the voltage divider connected to the non-inverting input of the comparator. Now we will derive the equation to find R1 and R3, which control the upper and lower voltage thresholds. We begin by writing two expressions for R1. This formula accounts for the low threshold voltage at which comparator resets. This equation represents the condition when the comparator just begins to trigger at the high threshold. To simplify the process, we set both equations equal and solve for R3. This leads us to a quadratic equation. We solve this for R3 and we have all the threshold voltages. So putting this into the equation, we get R3. The nearest 1% standard resistor value is 106 kilo ohms, and we'll use this for our one resistor. We'll round this to the nearest 1% value, which is around 31 kilo ohms. Now this divider generates 1.419 volt at the low threshold and 1.4421 volt at high threshold, making the comparator trigger accurately for minus 35 amperes and minus 31.5 ampere current levels. The second comparator is configured as non-inverting. This corresponds to output voltages of 2.31 volt and 2.44 volts. We can calculate the value of R6 and R7 using the same method. Now that we have R6 and R7, we calculate the voltage seen at the comparator input using a simple resistor divider. This is the voltage threshold at which the comparator switches states. We assume R5 as 10K and then calculate R4 to generate this exact threshold from the supply of 3.3 volts. So R4 can be selected as 4.64 kilo ohms. From this resistor will trigger alerts when current exceeds 100 ampere and drops below minus 35 amperes, and reset when current returns to safe levels between minus 31.5 amperes and 90 amperes. Let's see how this circuit works. The circuit starts with shunt resistor R8 placed in the series with the current path. As current flows either forward or reverse, it creates a tiny voltage drop across it. The current sense amplifier amplifies this voltage. So we get these output voltages at the different currents. Next, the amplified voltage goes to the window comparator made out of two TLV3201 op amps. This comparator is in non-inverting mode with resistor R4, R5, R6 and R7, which detects the 100 ampere overcurrent and resets when the current drops below 90 amperes. Now let's look in the reverse direction. This comparator is in inverting mode. It receives a reference voltage through a resistor divider formed by R1 and R2. We tune this divider to give two critical voltages. When the current goes below minus 35 amperes, it will trigger the overcurrent in reverse direction. and goes back to normal level when the current is minus 31.5 amperes. This hysteresis prevents the output from rapidly toggling between current hovers near limit. Well, there you have it, a complete breakdown of how to sense current in both directions and how to make your circuit smart enough to respond when things go out of control. I hope you learned something new from this. Don't forget to check the description from references. If you found this video useful, hit that subscribe button and stay tuned for more exciting content.